Okay, yeah, it's recording now.
Okay, great. So hello everybody. Welcome. Today we have an MSc seminar by Ohad Levy-Or. So briefly about Ohad. So Ohad finished his BSc degree magna cum laude from the Mechanical Engineering Department at the Technion in 2021. And he's been pursuing his MSc degree in TASP, the Technion Autonomous Systems Program, since 2022. Okay, go ahead, Bob.
Thank you very much. So yeah, as Vadim mentioned, my name is Ohad Levy-Or, and today I will be talking about my research titled "Novel Class of Expected Value Bounds in Applications in Belief Space Planning," which was done under the supervision of Associate Professor Vadim Engelman. So when we're starting to see in our world, both in research and in the real world, autonomy in all sorts of places. These applications being medical robots, drones, cars, just to name a few. And now when we start talking about these applications of autonomy in the real world, we also have to take into account uncertainty. Now, this uncertainty may come from many different places. It can be because the actual action differs from the action that the agent wanted to take, from noise or imprecise motor actuations. The measurements themselves can also have noise in them, and the environment around the agent can change over time, adding another layer of uncertainty around it. Now, when we're talking about uncertainty and autonomy, we also, and we want to solve this problem, then there are challenges that we have to address. These mainly being the computational limitations of what we currently have available to us, current technology. And additionally, most approaches that are able to tackle this problem are online approaches, which also limits the algorithmic approach to the problem. So let's take a look at one such planning approach. So the agent begins with some initial belief about its state. Now, the agent maintains a belief over its state because it cannot directly observe the state. And so it has to believe that the state is something, basically. It has a distribution over the state. Now, given this initial belief, it begins planning under uncertainty. Now, this will be an entire algorithm, but once it's finished processing, then the output is some action space or action sequence or a policy. Now, the agent takes the actions and performs them. It then gains measurements along the way. And finally, it needs to update its belief as the state has changed. So it updates its belief and the cycle continue again. So let's start by briefly talking about what the inference step looks like. So in probabilistic inference, we're talking about Bayesian inference here, and this happens in two steps. In the first step, there's a prediction step where the agent takes the old belief and predicts what the new belief will be just from the action. After performing the prediction step, the agent can update its belief or refine the belief to a more precise belief from the observations that it's taken along the way. Now that we've discussed the inference, now we can go on to discuss the actual planning problem. So a planning problem is oftentimes formulated as a POM-DP, or a partially observable Markov decision process. Now, what does this actually mean? Well, a POM-DP is given by the tuple with specified here, which we have the state space, observation space, action space. We have a transition model and an observation model. We have some initial belief and a reward that the agent would like to optimize. So if we're talking about optimizing a reward in planning, then oftentimes we have to discuss the expected reward. And when we add even a horizon, then this also becomes the cumulative expected reward, which is the value function. So if we look at the value function here, this is the recursive formulation for the value function. And we see that the value function is equal to the expected reward plus the expected subsequent value function. Now, the reward itself might also have expectation in it. We have the expectation over the state space for the reward, where the reward might be state dependent, or in a more general case, it might even be belief dependent. And what we know here, just from this slide, is that we have a lot of expectations that need to be taken in order to actually plan in belief space. So the question immediately arises, how do we take these expectations? So if everything's nice and linear and Gaussian, then an analytical approach might be possible. But oftentimes this is not the case, in which case we need different tools in order to tackle these expectations and perhaps even estimate these expectations. One such tool, for example, is Monte Carlo simulations. So while we talk about, when we're talking about the value function and optimization, then we talk about wanting to search for the best actions to take. So in order to do this, what we do is we maintain a belief tree, which is a data structure we create to assist us in reasoning about the optimal action. So in a belief tree, we expand the actions and observations via some predefined algorithm and up to a horizon of our choice. And now, given this tree, we can now use tree spanning algorithms to search for the optimal action or policy. So given what we've talked about so far, what are the challenges? Well, given all these expectations, the problem of finding the globally optimal solution is intractable for all but the smallest problems. And what prior works try to do is they find an asymptotically optimal solution, which doesn't necessarily have guarantees in any time. So what can we do? Well, we can do what we call simplification with guarantees. So what exactly is simplification with guarantees? Well, we take a simpler problem that is tractable to calculate, and we use known bounds to bound the difference between the simplified and unsimplified problem. And these bounds may come from different areas, and we'll see them from probability theory. And this simplification with guarantees, what is it actually good for? Well, we can use it to quantify how suboptimal an algorithm is, even when it does not select the optimal action necessarily, alongside providing anytime guarantees on an algorithm. And if the bounds are tight enough in some scenarios, we can even provide select the optimal actions. So what are examples of such bounds that might be used for simplification with guarantees, or even other bounds in POM-DPs? Well, one bound is Markov's inequality, which I'm sure most of you are familiar with. And the second is Hofting's inequality, which is probabilistic bounds. Both these bounds are bounds on random variables. So what are our contributions in this case? Well, we formulate bounds utilizing partial expectation, which is a notion that we will shortly introduce. We then utilize those bounds to formulate new Hofting-like bounds. We utilize the bounds to also bound the value function. And we formulate bounds on the conditional entropy, and even formulate bounds on Bohr's estimator, which previous works have which we've been able to bound with greater computational efficiency than previous works. Finally, we show how can you reuse information between similar belief topologies when calculating conditional entropy. So let's look quickly at what exactly is partial expectation. So the idea comes from the fact that instead of calculating expectation on the entire support, what if we could just calculate the expectation on part of the support? So if you look at normal expectation, we see that we require integration over the entire support. So if we look on the image on the right, we see that this would be all of S. Now, a partial expectation requires integration over part of the support or a subset of the support. So if we split our support into the subsets B and B complement, then we can perform our integration only on the subset B. Now, the exact definition of the partial expectation is given below. So how can we use this concept of partial expectation in bounds? Well, we formulated Markov-like bounds, and we'll see the connection to Markov shortly. Now we see that the lower bound is that the expectation is lower bounded, for example, by the partial expectation plus a correction factor. So what exactly is this correction factor? So if we look at the image on the right again, we see the area in blue indicates the partial expectation, where if we had to calculate the entire expectation, we would perform integration over the whole curve F. But instead of that, we perform integration only on the subset B, and that integration is indicated by the blue area. Now, what remains, the areas that we do not integrate over, we have to lower or upper bound respectively. So in the case where we discuss the lower bound, we lower bound the function in the complementary subset by the minimum of that function in the complementary subset. So quite simply, we see that the bottom of the red area, that's the minimum of the function in the complementary subset. And so we take that minimum and we just weight it by the measure of the complementary subset. And for the upper bound, we do a similar process. Now, the complementary subset can also be split further into multiple subsets for a more general bound, and this can be seen in the paper. So how is this actually connected to Markov's inequality? Well, if we assume that the function f is greater than or equal to 0, as is done in Markov's inequality, we quickly see that the partial expectation is also greater than or equal to 0. So this quickly leads to Markov's inequality, where we can lower bound our lower bound, and we arrive at the general Markov inequality. So what are the properties of the bounds that we've discussed up until now? Well, first off, we have convergence with respect to the subset, meaning that as the subset tends to the entire space, then we will converge to the expectation. We also have partial incrementality, meaning that oftentimes we can reuse calculations from the lower bounds to get tighter bounds, and we don't have to completely calculate the tighter bounds from scratch. Finally, we also have monotonicity of the bounds with respect to the difference between the expectation and the partial expectation. And all these properties are very beneficial when we discuss planning algorithms. So as we mentioned, we also apply these bounds to Hoeffding's inequality. So let's take a look how that looks. So in the case of Hoeffding's inequality, applying the bounds yields two novel probabilistic bounds. And we'll see why they're slightly different. So in the first case, we have our entire support S, and we sample from that support. And now, given all these samples, we now select a subset of the samples, okay? And doing so yields the following bounds. Alternatively, what one could do is we first select a subspace of the support, and then we sample only from the subspace, okay? And doing so results in the following bound. Now, the hat here indicates empirical expectation here. Now, in both cases, for both these bounds, there exist conditions for which our bounds are tighter than Huffing's inequality. Now, what do I mean by tighter? I mean that the difference between the upper and the lower bound is guaranteed to be smaller than the gap for Huffing's inequality. And each of the two bounds that we mentioned have different conditions. So we'll quickly illustrate one of these conditions. So the first row here is the condition, and then we define C, and we define this delta F. So I'll quickly describe what this delta F of B is. The delta F of B is the difference between the maximum and the minimum of the function on the support B. So if we look again at our image, we see that delta F of B complement is given by this gap of the green and red area. So what does that actually mean? It means that that this condition can be true for one subset B, but not true for another subset B, even though they might have the same measure. So this highlights the importance also of selecting the subset B inherently. Now, now let's go on to discuss how we can incorporate these into planning. Well, what are the challenges in planning, first of all? So in planning, some of the challenges that have yet to be addressed or that have been only addressed briefly because they pose such a big problem in planning are non-parametric beliefs, belief-dependent rewards, and high-dimensional problems. So let's see if we can address some of these with our bounds. So as we discussed initially, in planning, we have this value function with expectation, and we have the expectation on the reward. So we have all these expectations, and now clearly, after having discussed bounds on expectation, it seems very clear how we can directly apply our bounds to these expectations. What we notice, though, is that in the case of planning, the expectation can either be taken with respect to the state space or the observation space, which will yield different classes of bounds for planning. So let's start easy. Let's start with bounding the reward. So if we bound the reward with our bounds, we very quickly just arrive at the following bound. And if we substitute rho with some arbitrary function f, then this is exactly the bounds that we initially derived. But in this case, this is done for the reward, and the simplification is done with respect to the observation space. So let's go on. So this was very simple. Let's look at the value function. So the value function is, as we mentioned, the cumulative expected reward. So if we break down this culmination, this summation, then we can bound each expected reward separately. And that's exactly what we've done here, very simply. But perhaps, so although these bounds are valid, they might be a bit opaque, because what I see here is that we have here the infimum with respect to all past observations on the current reward, which might be something that's more difficult to grasp, and then also to formulate bounds on for a general algorithm. So perhaps we can do something better. And to do so, we'll start by looking at the recursive formulation of the value function. So by looking at the recursive formulation, we again are able to formulate new bounds. And then we have this very complicated bound here for the lower bound. But what I want to highlight here is these two. These two that to me again still look fairly opaque, and perhaps even this partial expectation over the lower bound. But again, we have here the infimum of the simplified value function and the infimum of the lower bound, which might be a bit more difficult to grasp and formulate into an actual algorithm in this scenario. So, but on the other hand, there are benefits to this approach. So the bounds are valid and do hold, and this approach does have its benefit, which might require future research. And this benefit is that if we look at the belief tree here, when we select a complementary subset to discard, what happens in the bounds that we just discussed is that we completely prune certain areas of the tree. So they get removed, and clearly the computational benefit of this is very great. But this comes at the cost of the ability to actually formulate these bounds. So let's look at something that it's a bit more transparent. So in this case, what we do, we again look at the recursive formulation of the value function, but instead what I want to highlight is that we bound, or simplify rather, only the expected reward. We've left the expected value function unchanged, and only the expected reward gets simplified. This means that the tree itself is unchanged. So we do not benefit from pruning branches, but for me at least, the infimum of the current reward with respect to the current observation is something that's much more manageable to work with when formulating bounds. So let's take a look at how we've done this for conditional entropy. So in the case of conditional entropy, we've also been able to formulate bounds. So this is an expect on the expected reward. But there are two assumptions that we've done here. The first is that we assume that the actions are independent of the observations. And the second is that we assume that the model infimums, meaning that the observation model and the transition models have infimums greater than 0. Now the actual bounds are given in the paper for those interested, but we'll continue on. So now we can go on and look at the Bohr's estimator. So the Bohr's estimator is given here. And what prior works have done is they've been able to bound this with O of small n big N. What we show is that we provide bounds of small n squared. So clearly there's computational benefits here for the bounds of this sort. But at the expense of, again, we require that the model infimums be greater than 0. And the explanation for this is fairly intuitive, because otherwise what will happen is we'll see in the bounds that we take the log of 0. And then we have here infinity or negative infinity, which leads to fairly useless bounds. Now, in the case of the Bohr's estimator, the simplification is done with respect to the state space. Now I want to discuss something slightly different. I want to talk about data association. So if we don't reason about data association, then what happens is that observation dimensionality can change, meaning that we may take one observation that may end up being from 2 landmarks, and at the same time take another another observation that might be from 5 landmarks. And so we see here that the problem isn't necessarily well conditioned if we don't take into account data association. So we need to do this when there are multiple landmarks that may be observed at a given time. And that will require us to reason about which landmarks we actually do observe. So to do so, we use the binary random vector beta to capture this data association. So what does this actually look like? Well, if we look at the image on the right, what we see are 6 beacons. So our beta will be of dimensionality 6. And in this specific case, we see that we get a reading from beacons 2, 5, and 6. And we can see this in the realization of beta on the left right here, where the indexes are 1, where the beacons with that index is, we get an observation from that beacon. Now, in parallel, we'll also mention topology, and we'll see also how this relates to data association. So topology in planning, or not even in planning, but for beliefs, is in the form of a factor graph. So a factor graph is a bipartite graph, or a graph that has 2 kinds of nodes, and it represents the relationship between the variables in the belief. Now, we commonly see these the use of factor graphs for high-dimensional problems, problems with a lot of variables, and we want to see the connectivity between them. So, for example, in SLAM. So now, how does this relate to data association? Well, given a specific realization of data association, we have a specific topology. So if we look on the right, what we see is we have here 2 data association nodes, which I'll briefly go into after this. But we have 2 different data associations. And so one data association suggests that we only see landmark L1. The other data association node suggests that we see landmarks L1 and L2. So we see here that data association dictates the topology of the factor graph at this time step. Now, what you've also probably noticed is that this isn't a regular belief tree, but we've augmented this belief tree with the addition of data association nodes, the triangles, where what we have is after selecting an action, we then expand and reason about possible data association. And only after reasoning about possible data association can we start to reason about observations. Now, again, in what we have here in these topologies is that these black squares are still random variables. They represent random variables because we still have not reasoned about the observations. So that means that these are not proper factor graphs per se, but they do still have the same topology as the factor graph that they will describe. So how can we use all this with simplification? Well, similar topologies share many of the same variables. And so if they say many of the same variables, perhaps they also share many of the same information and calculations. So we reason that similar topologies should utilize the same calculations or information. And we'll see how we do that for the case of conditional entropy. So here we have bounds on the conditional entropy given data association. And in this case, this bound is the conditional entropy of the data given the data association realization beta tilde. And we bound this conditional entropy with a simplified conditional entropy that incorporates information from the data association beta. And using that, we can formulate our bounds. Now, how do we see this? Well, our original topology is beta tilde, which is on the right here. And we use information from the topology beta. And so what does this mean? It basically means that we've pruned this realization between X and the landmark L2. Now, the significance of this is that it means that we don't even need to reason about the possible realizations of the observations between the pose and the landmark L2. So if that was bounds for the expected reward given data association for planning, we now want to see how we can take this further to use it for a Q function. So by looking at the expected reward, which is what we have the first term on the left, and we take into account data association, the expected reward looks as such. And if we use partial expectation, meaning we only take into account part of the data association, then we have this term here, and on the right side of the equation, we have all the data association that is in the complementary subset that we haven't taken into account. Now, what we see on the right-hand side is the green rectangle. And what this green rectangle encompasses is the expected reward given data association, which was what we were able to bound in the previous slide. So what does this mean? It means that we have now bounds on the expected reward. And if we have bounds on the expected reward, then if we go further back, we recall that we were able to use that to formulate bounds on the value function, and thus also the Q function. Now, as this was done for the recursive formulation of the value function, we can use the tools of Bellman optimality, and we can provide bounds on the optimal value function, and even as we initially mentioned, if the bounds are tight enough, select the optimal action, or in some cases, not select the optimal action, but still eliminate bad actions. So let's look at a scenario. So in this scenario, we have an information gathering task for an agent with 9 landmarks. Now, these landmarks are uncertain, and as such, we incorporate them as part of our belief. So we have to reason about them. For our simulation, we had a planning horizon of 1. Our action space is the cardinal directions, and it's a smoothing problem, meaning that past poses are added into our state. Finally, simplification was performed with respect to the data association space, as was discussed in the bounds that we just talked about. And the bounds are on an estimator of the conditional entropy. So not on the theoretical conditional entropy, but we had a particle representation, and we used that to formulate an estimator of the conditional entropy. So what do we see in the image? Well, we see the starting point in green. The red line indicates the ground trajectory that was taken by the agent. The blue intensity indicates the probability that the landmark will succeed in transmitting to the agent, meaning that even if the agent is close to the beacon or close to the landmark, an observation may not necessarily be gained because the landmark failed to give an observation. The yellow intensity indicates the prior landmark certainty in the prior belief. And finally, the black arrows are the argmax of the estimator of the lower bound, meaning from our bounds, we took the maximum lower bound, the action with the maximum lower bound, and that's the black arrow. So in this specific case, we see that the action taken by the optimal action and the bounds selected the same action, and the inconsistency here is only because of the noise from the transition model. So what do the results look like? Well, let's begin first by introducing kappa. So what exactly is kappa? Kappa is the approximate fraction of the data association space that is calculated. So meaning if kappa equals 1, we still calculate all the data, we take into account all the data association, meaning we don't eliminate anything. Alternatively, if kappa equals 0, we eliminate all the data association, and that also means that we eliminate all possible observation realizations. And so the only thing that we take into account is simply propagating the belief via the action. And if we use something in between, then we take into account only part of the data association. And so what we see, and also what's intuitive, is that kappa is directly proportional both to the runtime and to the bound tightness. So as we take into account more of the data association, we get tighter bounds, but at the cost of runtime. So let's look at the image on the right. What we see here is an illustration of the Q function. So for each action, we have a value function. And let's look at one of the value functions, or the Q functions, for a specific kappa. So for kappa equals 0, meaning for the blue image, for the blue bars, what we have here is very loose bars, very loose bounds, which we intuitively understand because we don't take into account almost any information. But if we look at the runtime on the left, we see that our speed up is times 40. So we have an incredible speed up with respect to the explicit expectation, but at the expense of very loose bounds, which perhaps we can't do too much with. When we look at kappa equals 1, we see that the bounds converge to the value function, which is what we would expect. Finally, for the intermediate values, we get tighter bounds, but that don't necessarily converge to the value function. But what's nice, and that I would like to illustrate here, is that, for example, for kappa equals 0.5, meaning if we look at the green dots, and specifically, let's look at the action -1, 0, and 0, -1. What we see is that the bounds don't overlap at all. What does this mean? It means that the action 0, -1 is guaranteed to be suboptimal with respect to the action -1, 0. So clearly, even when taking into account kappa equals 0.5, this still allows us to discard some of the actions, but perhaps still not select the optimal action. And if we look at the speed up of these respective intermediate kappas, we see that we get speed ups of 1.3, 2.6, which is still very desirable. So what are some open questions that we still have? Well, from an analytical point of view, not talking about planning, how do we select the best subset from all the possible subsets of a given measure? So if we look at all those subsets, which will give us the tightest bounds? The question again arises, though, for planning in online scenarios, in which case perhaps the results from finding this optimal subset might not be tractable to find for an online algorithm, in which case perhaps heuristics for finding such a subset might be utilized. Now, we discussed using a reference beta or a reference data association in our bounds. But in our implementation, we didn't go too deep into how do we actually select it. We just oftentimes selected the simplest beta. But perhaps there's more to be done here. Perhaps the reference beta can be selected in a more knowledgeable way. Something additionally that should be addressed is implementation of a full adaptive planning algorithm with our bounds that allow for selection of the optimal action, where in the beginning we discussed the properties of these bounds that are beneficial for planning algorithms, and perhaps we want to see those actually utilized for planning algorithms. Finally, we didn't discuss at all how the Hofting-like bounds that we formulated could be used in planning. So that would be another avenue that future research should discuss. So this is a summary of the points that we discussed, and thank you very much for listening.
Thanks, Ohad, for this interesting seminar. We have time for quick questions if anybody has question now. All right, so in this case, thanks again, Ohad, for this seminar, and hopefully we'll see each other soon in the next seminar. Thanks a lot.
Thank you.
Bye-bye.
Bye.